Okay, everyone, our guest speaker today is Aline from Department of Obs and Gyne. First met Aline in a class called CPSC 540, which I now teach. We didn't do our lab project together, but we studied together. So she did her master's and PhD with a combination of Kevin Murphy, Paul Gustafson, and Nardo Doucette, some of who are still at UBC, one of who is still at UBC. And so now you've gone off and done work in tons of areas, so not just Gaussians anymore, but privacy and this endometriosis, is that the right word? And lots of other things. So let's welcome you.
Thank you everyone for coming. I'm really excited to talk to you this afternoon about LEAP. So LEAP stands for Large Scale Federated and Privacy Preserving Evaluation and Analysis Platform. So it's a mouthful, but I'm not going to say that again anymore this talk. So I'm just going to call it LEAP. So what I'm hoping to do today is to briefly talk about some of the barriers to AI and machine learning in health sciences and health research and medical research. I want to outline some of the issues particularly relevant to data sharing, and introduce differential privacy and federated learning, present LEAP as a potentially deployable distributed system to do private data analytics, and then discuss next steps. So AI has lagged behind other, AI in medicine has lagged behind other domains. And while this is true, it's everyone agrees that it's going to have a profound impact in medicine. So we've already started seeing lots of application of AI in medicine, particularly around imaging and diagnostics, precision medicine, personal health assistance, and drug discovery. So a recent Lancet article reviewing deep learning algorithms for disease diagnosis from imaging has sort of concluded that these deep learning algorithms are at least as good as healthcare experts, but they're 1,000 times faster. Though everyone knows that deep learning algorithms are data hungry, so in order for ML and AI to be effective, they require lots of data, and big data is defined by volume, velocity, variety, all of which are present in medical data. So we have lots of it, and it comes in all sorts of forms, and definitely it's it's coming in very rapidly. So why is it that even though data is everywhere in healthcare, we're still not seeing sort of the impact of AI and machine learning? So first of all, not all of data is electronic. So maybe this may come to a shock to some, but those of us who work in the healthcare system know that that's the case. A lot of it, like paper charts, still exists in many cases. Sorry. And even if the data is electronic, or it comes in an electronic format, does not necessarily mean it's machine readable. So I'll give you a very good example to that. Physician dictated notes, clinical notes, are transcribed and then uploaded as digital images that are not machine readable. So that's a very good example of data that could be, but is not. And unfortunately, the data that we're seeing is coming in a variety of shapes and forms. The data is also fragmented. So even though in a system like the Canadian healthcare system, where we have a single payer system, one government that pays for everything, you would think that all of our health records are in one location. They are not. They are at the different health institutions, and then furthermore, they don't talk to one another, and they require data sharing agreements to talk to one another, all of these different institutions. So for example, VCH does not talk to BC Cancer, and does not talk to, for example, St. Paul's Hospital, because they're all on different systems. The data also is not interoperable, and furthermore, they cannot even agree on the semantics to use. So different folks want to use different types of semantics to refer to different things depending on what they're using the data for. And so that's been one of the key issues in why this data has been not lacking interoperability. There's also a possible bias that's related to recency. In recent years, I think the statistic is like every year the number of health data has increased by 10-folds for the last 3 years or something like that. And then obviously the data that you're likely to encounter, if it's digitized, is going to be more recent. And then finally, privacy, security, and ethical violations are a huge concern with data sharing. So in today's talk, I'm going to focus, while all of the other topics are very important, and lots of folks are doing great work to try to sort of bridge the gaps, my talk is going to focus on privacy, security, and ethical violations in data sharing. I started thinking about this problem when one of my colleagues, Dr. Paul Young, who is a gynecologist and a surgeon at Women's Hospital and treats endometriosis, came to me in my capacity as Director of Informatics with OFCare to basically design a network, to network different centers that are studying endometriosis together so that everybody can share, to create like this shared network. And then that's when we started thinking about the questions of privacy, security, and data sharing. So first of all, let's talk a little bit. Let's talk a bit about endometriosis. So what is endometriosis? So endometriosis arises when tissue from the uterus grows outside of the uterus. It's a condition that impacts 10% of women. So about 1 million women, Canadian women, are impacted by it. It causes infertility and very debilitating pain that sometimes starts in adolescence. The 10% statistic is most likely an underrepresentation because it takes a really long time to diagnose endometriosis. Currently it's between 7 to 11 years. And it's an understudied disease. But it has been linked with malignancies such as ovarian cancer and coronary heart disease as well as autoimmune disease. So it was a pretty important one. And then there was another reason why this became our sort of de facto pilot project for building this shared data network is because, first of all, it was a very specific project that allowed us to sort of limit the scope of our work. And it has potential for a very high impact, again, because it was not studied and there was not a lot of data on this. And Canada actually is emerging as a leader in endometriosis research. We have several centers that sort of recently popped up around the country, and there's like an organization that meets. So there's a very strong grassroots support from the community of clinicians to sort of support a venture like this. And furthermore, UBC particularly was involved in the creation of data standards for endometriosis that have been adopted worldwide, and we proceeded to create one of the first Canadian prospective data collections that adopt the data standard. So currently we have about 4,000 patients in our database, and we're accruing at a rate of about 1,000 per year. So what was our goal? Our goal was to adopt a socio-technical solution to facilitate data sharing, enable AI and ML, and analyze distributed medical data while guaranteeing patient privacy. So that was what we had set out to do initially, and so we started looking at what's out there. And then we looked at the model that's currently adopted for multi-center studies in present-day health research. Generally, that requires centralizing all of the data into one location and analyzing it. And with that, so first of all, there's the inefficiency we just talked about, the need for big data, inefficiency to move data around as the data gets bigger and bigger. But furthermore, and more importantly, it requires data sharing agreement, it requires consultations with ethics review boards, and those could be very, 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 very long and painful. I'm not sure if anyone in the audience has ever gone through something like this, but these could take a very long time, months, and they very well could possibly not approve them. And so initially I was really confused by this, actually. I sit on the research ethics board at the BC Cancer Agency, and I was wondering, like, these are all fellow scientists, and they're, you know, ethicists and people who really care about the patient. How could they not want data to be shared for the greater good? But after you think a little bit about it and you explore the risks, it becomes very clear why there is this, why these problems exist. So first of all, let's start with, you know, the good things about data sharing, which is undeniable. Obviously, it gives us powerful ways to evaluate what works and what doesn't work and how to improve care. It also helps us eliminate medical errors and waste, so we have a more efficient healthcare system. It helps us improve diagnoses and timeliness of diagnoses, which is fantastic. It helps us provide the right treatment for the right patient at the right time, the promise of effective medicine. It provides us an opportunity to create a learning health system where everyone's encounter creates an opportunity for an improvement in care and evidence-based science, medicine. There's also the concept of open science, something that's often promoted and advertised especially by funding agencies who'd like to see, you know, especially research that's been sort of funded by public dollars, made available, publicly available and openly accessible. So those are all good things. Now, the bad things about, or the concerns with data sharing. So there may be harm that results directly from data sharing. So this is actually, you know, this could happen. If someone's identity is revealed, or if someone shares their data and then their identity is revealed, you know, there may be stigma associated with with the knowledge of others of one's disease. So for example, someone's HIV status becomes known to others. That could be something that they don't want. There could be financial harm. For example, denial of insurance coverage. There could be emotional distress. Someone's identity, like caused by identity theft, for example. But there could also be other ethical concerns that are not directly caused by harm to an individual. So for example, you know, just as an example of a situation like that, just imagine a chatty nurse talking about someone's cancer at the water cooler. This is an invasion to the patient, and it may be seen as loss of control of the patient. Also, how the data is collected is a bit problematic, because traditionally the sort of gold standard for data collection in health sciences has been informed consent, where the patient is told about, here are the, you know, you participate in the study, these are the risks. Now, in the age of AI, how could one tell someone what the risks might be? It's very hard to know what's going to happen, what we're going to do with that data, let alone to really be able to articulate what the risk may be. Also, who has access to the data, right? If I give you a data set and then you end up losing your laptop, does the patient have any control the patient loses all control. So open access is also not necessarily really good. Even when you de-identify data and you host it on a public repository, that may cause a problem, because, you know, as we'll see later, a lot of these data could be re-identified. And then finally, the biggest question is who owns the data? I mean, it's still unclear in Canada. I mean, if you ask the Health Services Authority, they'll tell you, we own the data. But does the patient own the data? Or do we merely have access to the data but not own our own data? In the United States, actually, the legislation differs between states. So different states think differently about this topic. So surely there must be some sort of a legislative, some law about this. So there's actually, in fact, there is. So in the United States, it's called Hipaa. We have a similar one in Canada. It's called FIPA. And there's one in other countries, like in the UK, it's GDPA. I'm going to focus on North America, so I'm going to talk about Hipaa. And FIPA actually mirrors it very closely. So what does Hipaa say? Hipaa says, actually has rules that says, identified data can be, sharing of identified data can be very restrictive. So there are certain scenarios where sharing identified data is okay. Quality control, that sort of thing, that's okay. But not, for example, for academic purposes. So if you did a quality control study and learned something, you could not publish on that study if it was done on identified data. But it allows, if we strip personal health identifiers, so there are some like 20-some fields that Hipaa decided are personal health identifiers. If you strip those and you de-identify the data, you could then share those for the purpose of research. But Hipaa only applies to healthcare providers, covered entities. And so those covered entities are physicians, hospitals, and hospices, or really healthcare folks. Hipaa only applies for healthcare data, but not health data. And we'll talk about that in a second, what that means. Finally, Hipaa doesn't really prevent hospitals from selling data, provided it's de-identified. But it has been shown time again that most de-identified data can be re-identified by linking it to other data sets. And that becomes more and more the case as data sets become larger and larger and multidimensional. Linkage attacks become very, very, very easy. And I think there was a study that says, all you need is 3 or 4 fields to re-identify about 87% of public de-identified records. So that's a bit concerning. What's most concerning, perhaps, is how little Hipaa actually covers. So this is a nice picture that tells you, so the tip of the iceberg, so anything above water is what is covered by Hipaa. So these are covered health information generated by Hipaa-covered entities. So just to give you an example, so you go in and do an echocardiogram at your doctor's office. That data is covered by Hipaa. You do an you do one on your Apple Watch and it gets sent to Apple. That data is not health data and it's not covered by Hipaa. Actually, there's another example, and it's about this app called Ovia, which tracks fertility and pregnancy in women. So women are asked to track information about their menstrual cycles, sexual activities, and that sort of thing. And then that data is not health data, even though it should be, and it's not covered by Hipaa because that company is not a covered entity. And what actually this company was in the news recently because they were sharing this data with the women's employers. And so what's wrong with Hipaa, actually? Well, one of the issues with Hipaa is that it was enacted in 1996. At that time, technology was very different than what it is today. And so it may be time for revisions, and I think that that is in the plans. However, for the purpose of our project, we decided that we're going to look at more current techniques for privacy preservation. And so one of the first things that we've considered is federated learning or distributed learning. So with federated learning, the data remains local for each site and it's never transferred. And it remains where it was collected behind institutional firewalls, and only aggregate statistics and model parameters are shared. So what that means is when a user has a query to make about a certain health data, they go on a cloud service, they write out their query. It could be, asking questions about how many cases are at different locations if they're trying to build a cohort. It could be trying to do simple correlative studies, or it could be something as expensive as doing building a predictive model. And then once they basically determine what their query is or what the task that they're interested in doing, that task gets distributed to all of the different sites. The computation is run locally, and only model parameters are shared and aggregated back. And so this way, each site could remain in control of their data and impose whatever security standards they're interested in locally. And there's a sort of global benefit from the learning from the data. So this is great. This sounds fantastic. So does it work? So maybe, you know, we're convinced that healthcare data should not be centralized, and because it's, you know, not only is it more efficient, but it gives each site more control of their data. And also we maybe, you know, federated learning is the sort of state-of-the-art approach for decentralized data. But, you know, unfortunately, even data, even with federated learning, we do not solve the privacy issue, because there could still be privacy could be still leaked from summary statistics, and data sets could be reconstituted from model parameters. So then what's next? Differential privacy has been hailed as sort of the next, it has been hailed as the sort of the next paradigm for privacy, for privacy in general. So what differential privacy does, it addresses the paradox of learning nothing about an individual while learning useful information about a population. As a quote from Cynthia Dwork, who is one of the first people, among others, that sort of started working on differential privacy. So what does that mean in practice? So here, I'd like you to meet Michelle. She is a patient of Dr. Young, and she suffers from endometriosis. Now, Dr. Young would like to enroll her in his study and collect some information on her, and some of that information is prospective longitudinal data. It's surveys that talk to her about her levels of pain, fertility, and that sort of detailed information, and it follows her over time. So Michelle knows that endometriosis is understudied and is a big supporter of research, but she's concerned. So she worries that based on published results from the study, someone will be able to learn some private information about her that she does not wish to be revealed. So what differential privacy does is that it provides a guarantee that the published result from Dr. Young's study will be about the same whether Michelle participates in that study or doesn't. And so what that gives is what is sometimes referred to as plausible deniability. So we could never ascertain for sure whether Michelle was participating in that study or not, and that is guaranteed. So the mathematical definition of an epsilon dp result should satisfy this ratio, which is that the ratio of a result obtained on a particular data set using a privatized query, whether or not the data set included Michelle's data or not, should be below a constant e to the epsilon. And from this, we could see the tension between the utility. So you can see that as epsilon approaches 0, so e to the epsilon approaches 1, there's not really a lot of information, that the data doesn't have a lot of utility. So Michelle's data does not add very much. And as e to the epsilon gets large, the privacy cannot be guaranteed. And here's like a really nice visualization of how as epsilon decreases, the clarity of the picture and the noise of the picture starts increasing, meaning that it becomes more and more difficult to identify the person in the picture. So this gives us the definition of what needs to be satisfied in order to have an epsilon dp query. How to privatize queries now. So typically, that involves injecting noise. So what is returned? Instead of returning the actual result, we return a perturbed version of the result. So it's the result plus some noise that's generated from a random number from a Laplace distribution with spread determining the amount of noise. So here, if the variance is large, or the spread of the Laplace distribution is large, the distribution becomes flatter, and if it's small, the distribution becomes more peaky. And this spread is generally a function of the global sensitivity of the query, and that's a function typically of the query and of the data set. And again, I'm trying to stay at a high level without going into too much explanation. But so the spread of the Laplace distribution is a function of the sensitivity of the query and the epsilon, which is the analyst sets that the parameter. So I'm going to skip over that slide. So some of the nice properties of DP. One of the nice properties is the post-processing invariance. So anything that you do to a DP result remains DP, which is really nice. Composition is also a very nice property. So in other words, if you combine together two DP results, the result would also be DP. And furthermore, you could quantify the loss of privacy. And so that is really nice because it allows us to compare algorithms. So given a budget set of privacy, which algorithm is more efficient? And that's really good because the fundamental law of information recovery states that overly accurate answers to too many questions will eventually destroy privacy. And so in order to continue to guarantee privacy to a patient, once this privacy budget runs out, the data set should be retired for that analyst. So the privacy budget is actually linked to an analyst, and so once that budget runs out for that analyst, they are not able to analyze that data set anymore in order for us to continue to provide the same levels of privacy guarantees. So this is great, but also really nice, the fact that it is not just anymore in the academic setting. This has really been applied in many, or used in many real-world applications. So for example, the US Census in 2020 is going to be using differential privacy. And the US Census is used to allocate federal funds. So obviously, they seem to think that the results that are coming out of differential privacy are accurate enough for these types of tasks. Other tech giants, the iOS and macOS, Google, Microsoft, Uber, On the Map, Harvard has a nice tool for differential privacy, and there's a TensorFlow privacy package. So all of these things indicate that this is a really active area that shows a lot of promise. So then, what about healthcare? Who's developing? Is anyone developing anything for healthcare? So we've looked around, and obviously, health research networks have been sort of thought out before, and the idea of distributed computing is not novel in health research. Systems like I2B2 and Shrine, Data Shield, these are all systems that sort of are built on the same idea, so decentralized data and aggregating and sort of distributed computing. However, not all of them have differential privacy implemented. And furthermore, they're a little bit restrictive because they try to impose a data model. So you have to either buy in to their whole data model and their whole data, basically, organization schema, or you cannot use them. And we're thinking, what is the state of healthcare today? It's Excel spreadsheets, right? Like there's a very, very big barrier to entry into these systems, and so there's a need that's being unmet. So the innovation we wanted to do with LEAP was the following. So first we wanted to implement privacy by design and by default. So in other words, privacy is not an afterthought. It is what we build the whole thing around. We want to use DP to limit privacy leakage. And we want to make all source code and artifacts from LEAP open source, well documented, and easily deployable. And we want to integrate with existing solutions. In the healthcare world, REDCap, which stands for it's an electronic data capture system that's been sort of proposed by Vanderbilt University, made freely available for use, has over 1 million studies, healthcare-related studies. And so it would be nice to integrate with these systems. These are the systems that are currently being used. So having a solution that sort of works with those systems and maybe even Excel would be fantastic. We also wanted to make sure that we talk with everyone. We didn't want to build something that no one uses. So we did a big stakeholder engagement campaign where we talked to patients. Well, since this is, they're the ones that are going to be impacted by this the most, we wanted them to be at the table, helping us make decisions, set priorities. We also engaged with ethicists and privacy advisors from across Canada because we want this system to be used at health institutions. And so in order to do that, we need to start socializing ideas of privacy with different folks from different parts of the country so that we're able to implement this in practice. We also wanted to talk to hospital IT folks so that they could tell us what is required and what is feasible and what isn't feasible, and so that we could understand the limitation from their viewpoint. So we've envisioned a system that is accessible by different users, patients, researchers, administrators, that are able to log into the portal and do a variety of different things. So for example, patients can look at their own health record, they could look at their own data, they could look at patients, they could discover patients like me and see what works for them. Researchers could go and run their models, and administrators would make sure that everything is kept in order, everyone is accessing what they're supposed to access and not accessing, and logs are kept in order, and that sort of thing. Furthermore, we've envisioned a model that is distributed so that each site remains in control, each health site that's connected to the system remains in control of their own data, and nothing is shared. So we've implemented the LEAP. So the current status is we have a prototype that is available, and it's built in Python and Go. It's programmable via an API, and it has differential privacy implemented on some algorithms like count, mean, variance, federated learning with deep neural nets and SGD. We also have security that's been, some security features that have been implemented, like encryption and adversarial test cases. So the way that we've sort of designed the LEAP, the approach that we've adopted with LEAP, so each of the sites that you see here has their own little local LEAP computer that does the local computations. So each LEAP computer registers with the LEAP cloud. The cloud is responsible for authenticating users, distributing queries, and aggregating results and returning them to the user. And here the users have, there may be different users with different roles that have different sort of access privileges to the different data sets. Once we've built this, we've held a little workshop and we talked to researchers and we've tried to socialize some of the ideas of would this be something that's useful for analytics. And so we talked about the different types of analyses that we could do with LEAP. So obviously, the state of the world today is like unrestricted access to centralized data that's de-identified. And then obviously, they really like that because it gives them all the data all at once and they're able to really interactively explore that data. Then we explained about the possibility of access through like a federated API similar to Leap. So for example, the data stays at, you don't get to see all the data all at once. So they like that a little bit less, but you know, they still like the fact that they're working with the real data and they're getting access to it. We also asked them about, well, what about if we created some synthetic data and sort of added some differential privacy to it and gave you that data set? Would you like working with that? And they thought, yes, we would like it for certain things, but not everything, because when we're building a model, particularly in healthcare, I want to be able to validate that model on real data. It's not enough to have the synthetic data. And then, you know, finally, you know, what about the federated data with differential privacy? And people were like, okay, this is too restrictive. And so we went and started exploring the different privacy and security. We sort of tried to categorize them based on the following characteristics. So the type of data, type of queries, the number of queries that an analyst can do, how the data is accessed and transferred, where it's stored, and whether or not it has revocation rights. And we tried to sort of assess privacy and security based on these characteristics. And then you can see that the current model is really low. And that's the model that we have right now. So even with all of the Reaiiy and the Hipaa and all of that, it's still a model that leaves us really vulnerable with respect to both privacy and security. And then as we move down this list, you can see that, you know, now we're starting to get more private and more secure data, with the synthetic data and Leap DP being the highest for both. So what does that mean? What are the next steps for our project? So first of all, we would like to continue to build out the Leap prototype. We want to make it more usable, build out the GUI. We want to introduce more machine learning and DP, more models that have differential privacy. We want to implement the privacy budget and ways to optimize it. We'd like to start building out the integration with RedCap, because we think that that's going to really help us with uptake. And we would like to be able to deploy this on the cloud and integrate with other languages like R, which is very popular in health sciences research, as well as improve the scalability, security, and fault tolerance. We also want to try to demonstrate how Leap can work on a real application. So we've been sort of working a lot with endometriosis and the endometriosis team. We actually have researchers from 4 different Canadian medical centers that are ready to deploy this in their center, and we're just applied for a grant and we're waiting on the funding to start doing that work. We also have a center in Seattle at the Fred Hutch that's also wanting to deploy it. And then one of the first projects that we'd like to do is using those effects data, try to do phenotype discovery from the effects data to sort of try to identify what are similar characteristics of patients, and to see whether or not these are better at determining the ones that are determining the patients that are at higher risks of developing malignancies. We have also another application that is really interesting, and it's one in digital pathology, where we're trying to look at histotype diagnosis for ovarian cancer, and we're trying to evaluate whether using deep learning with real versus synthetic data under federated or centralized model makes a difference in how well we're able to classify these cancers. We're also continuing on with engagement. We have different stakeholders. So the first group is the patients. We want to continue to elicit their opinions about privacy and data sharing. Again, they're going to be using Leap to access their data, and to our knowledge, this has not been done in any other research system for medical data. So generally, you're not able to query your own data, and you're not able, furthermore, to look at what other people's data looks like. And then doing this in a private way is a really nice challenge, and we're super excited about that, and so are the patients. We also want to promote DP with the research ethics boards in different hospitals with privacy and regulatory folks. This is something that's fairly new and has not been really broadly advertised, so it requires a little bit of marketing and promotion, and we're hoping to do some of that by looking at ways to communicate differential privacy to lay audience or just even scientific audience that does not have or is not interested in the mathematical underlying characteristics of DP. I would also want to introduce the LEAP team. So this is not just this has been the effort that's been culminating over years. Paul Young, Holly Longstaff, Ivan, and myself have been working on this since 2017, when we started thinking about LEAP for endometriosis. This really did not become real until we hired superstar students Matt and Chris, who built out the prototype over the summer and made this real. Over the summer as well, Matthias joined us. He has expertise in differential privacy, and we're really excited to have him on board and flesh out some of the ideas that we have. Paul has built a very extensive clinical network that includes clinicians from different hospitals and patients. Aliba Shashati is leading the digital pathology work, and we've been collaborating with everybody who is interested to lend us a hand. I'd like to just take the opportunity as I end this talk to invite you to join our team. So we are looking for collaborators, anyone who is interested in the intersection of machine learning and differential privacy, anyone who has interest in human-computer interface, privacy and security, ethics, patient engagement, communicating concepts of privacy and or anyone with data who wants to try it through LEAP. We're hiring students, undergrads, masters, and PhDs. So if you're interested, please talk to me. Thank you. Yes?
I see some similarities with the open source project PySIF from OpenMind. So have you heard about it? And if yes, can you tell us why, if you could, what's the difference?
I have not heard about it.
Okay, I can.
But we will look into it. Thank you.
Okay.
Yes.
Can I just ask concretely how the differential privacy works? So I understand the general principles. I'm trying to wrap my mind around how I guarantee that the probabilities of identifiability with and without, and how you could compute those. So for example, with the image where you add the noise, how much noise you can add to an image before you can identify that person. That threshold is just constantly changing as algorithms develop and improve, and denoising algorithms, and I guess, yeah. So just concretely, how can one how can one come up with that number?
Yeah, so that's an excellent question, and in fact it's one of the most difficult questions.
Okay.
With this sort of work. And I think that this is one of the things we would love to tackle, is to come up with a way to sort of make that number mean something. And so one of the ways that we're thinking about it, and again, we're not really there yet because we're still thinking about this. This is really very, very new to us. But one of the ways we're thinking about it is the probability of re-identification. If you say, okay, so what is the probability that I could re-identified from a population of 1,000 or 100,000,
Yeah.
and think of it in that way, and then that sort of map that to the epsilon, and that allows people to make some sort of choice that's less arbitrary.
But does that need to be conditional on the algorithm that's being used for the identification, and that's a moving target because it's.
Well, I think what happens is that you set what you want the privacy to be, and then based on that and the privacy budget, if the algorithm uses up a lot of that privacy, then your budget runs out faster. And if it doesn't, then you'll have more queries to run.
Oh, okay. So as an individual running queries on the system, okay, you might have a certain budget of queries. Okay.
And then the other thing that we're thinking about doing.
But I could be collaborating with my friend here, and I'll get him to send in a few queries, and I'll collaborate.
Yes. So that does assume that no one's colluding.
Okay.
So yeah, we are making some assumptions that we are basically going to try to, as we move forward, try to sort of loosen them and try to test out different scenarios. But yeah, we're assuming that people are not colluding and that people are generally honest. They may be curious about things, but generally honest but curious.
But is the general idea that I get X-rays or images or data sets with Gaussian noise added, or is the general idea I'm just trying to see, is the general idea that when I run a query, do I drop some data points, or am I adding noise, or those are all options as long as the final DP constraint is the holds?
Yes, so it depends on what you're trying to do. So say what you're doing is you're exploring cohort availability. So you're trying to see if there are enough cases for you to build your model. Let's say you're applying for a grant, and you're trying to see that. Getting a very accurate number at that point is not really crucial, right? So you crank up the dial, and then you don't waste your privacy budget on that. If you're doing some exploratory analysis, maybe you just want to download the synthetic data and play around with that. And that does not eat up some of your budget. And you can do unlimited exploration with the synthetic data before you go into the real data. So again, I think the whole idea of how are we going to design this to optimize the privacy budget so that people could do more queries, or run more queries and get as much utility without ever compromising the data. We've also looked at ways to partition the data, so you could only work on certain partitions, and when you've sort of, your budget expires, we remove that data set and you go move on to the next partition, and so on. So we're thinking of different ways.
So there's many different models that might be.
Yes, exactly. And so those are all ways that we're thinking about optimizing the privacy budget to allow people to work for as long as possible without cheating. Yeah. Yes?
I had a question about the big table you had with 4 different rows and columns.
Yeah.
I think one column is missing. So you had the first row saying the analyst has unlimited queries.
Yes.
But in differential privacy, you limited it to the budget.
Yes,
right?
with differential privacy, you're limited with the number of queries to the budget, for sure.
So if you have 4 different hospitals,
Yeah.
and they're aggregating their data, do they still have unlimited access to the global data set, or is it local data set?
Okay, so it depends. So let's kind of walk back. So let's say we have 4 hospitals, and they each have a data.
Right.
Each hospital has data, and you're the analyst, and you don't belong to any of these hospitals.
Okay.
But you've sort of signed up to the system, and they accepted to give you access, and they gave you a budget for your privacy. Now, okay, hang on. Even before that, so they've accepted you to the system. So say there was no privacy, and you're just basically, everybody's allowed to get access to all the data, right? So the case with, let's say, TCGA, for example, if you're familiar with that data repo. But anyway, so any public data repository that gives you access to everything, no limits, then you could do as many queries as you possibly want, right? Like you're not limited by anything. And that's problematic, obviously. Now, if the data stays federated, but we don't have any DP, that data is still the actual data, but now you're not getting full access to it. But you still do as many questions. You could still ask as many questions as possible, right? Like you're not limited by how many the number of questions that you ask of the data, even though it's distributed, it's not limited. Once you start adding differential privacy to this, now you have a budget that you're assigned, and you could only ask questions for as much as the privacy budget allows you to ask. After your budget runs out, if there's no, if either you move on to a different data set that's similar, has similar characteristics, if it's available, if it's not available, game over, right, for you as a researcher. So I think those are those are the nuances. Now, with the synthetic data, this could be a way to give the researchers a little bit what they want, which is access to all the data all at once, so that they could try to build fit models and build models that are a little bit less piecemeal than doing it in a federated or distributed way without using up their budget. Yeah.
How does the RUB process fit into that then? If you're already given that budget, do you have to go on top of that and get approval from your ethics board, or?
So this is very interesting because we have no idea how ethics boards are going to react to this. So one of the things that we're trying to pass with the ethics board is to say, well, actually, we don't even need ethics for this because the data is not being moved and nobody's actually seeing any identifiable anything. So even the model where it's federated or distributed, that model is already way stronger than what we're currently allowing, right? And so maybe that does not require as much ethics, or maybe there's like the system has ethics and you're just basically filing like a, like there's a template that you fill in and file just to basically have a log of what you're using it for and that sort of thing, but nothing beyond that. So we're trying to sort of, I think it does not require as much ethics, just because, again, the technical solution is just so powerful that it's overwhelming what we currently have. And so if we can do what we can do today, this should be no problem. Yeah.
Right. With a lot of imaging-based projects, there's a lot of pre-processing of the imaging data that's required. So all of that has to happen before any deployment or your testing of your machine learning models. How is that supported through a framework like this?
So again, I think the idea of, we've thought a little bit about data cleaning through the system, and I think this is interesting. We don't know how to do it, so those are some of the things that we're going to try. But one of the things that is interesting is that each site is still independent and they have access to all the data at the site. So let's say they've decided, or maybe there's a study that's running and then we decide that we're going to run this data cleaning algorithm, then that could potentially be sent to all the sites and it runs. Or maybe there's some local data curation that happens, and then that gets uploaded offline. And then, but then again, this is where you're sort of starting to trade off between, local access versus doing the same thing and reproducibility and that sort of thing.
Mm-hmm.
Also, like the way the programming model was made, you have like these different functions, and like one of the things that you can write your own pre-processing or post-processing algorithms that you can like push to the site, and then you can have customized pre-processing.
Yeah, because that assumes that all the sites will have the proper dependency.
Yeah.
Okay.
Yes.
Yeah. So I was wondering, you were talking about some of the problems that you currently have with fragmented data, that there are like multiple data pools in different care facilities. And I was wondering, like, does LEAP help to integrate data of one single patient? Like, would it help a single patient if that person moves from one care facility to another care facility, and you would like to track their medical data and just like see what their path through the healthcare system looked like?
Currently, in our present implementation of it, which is like basically version 0, it assumes that a patient is only in one of the hospitals. So if they move hospitals, we kind of lost track of them unless they've reconsented in a different hospital, and then we recreate another record. So that's obviously something that you could sort of expand on as this becomes, so right now it's basically a research system. As this scope moves on to become clinical system, for example, that might change. And we are sort of working to make it. I think the real benefits from a platform like this will be realized when it becomes a clinical system, and we are trying to sort of work with members of the industry to try to see, well, once we've built the prototype and we show that it could work, can we sort of take it to the next level and make it clinical? And so now you have a unique identifier for a patient, so if they're moving, you continue to track them. But right now, I think they have a study ID. When they leave the province, let's say, and go to another province, even if they join, they'll have a different study ID in the different province. Does that make sense?
Yeah.
Is this consented?
So currently, yes, all of these patients, in endometriosis, at least the example that we're working with, they're all consented.
Okay.
And for the digital pathology, I think we have a waiver of consent. So we are okay to work with the data.
Mm-hmm.
I mean, I think eventually, I believe that every patient should have access to their medical record. I believe that every patient should be able to log in somewhere and see who's looking at what of their data, and they should be able to do that. And I think that's sort of the long-term vision that we're sort of working towards.
I did forget to preface my question, my earlier question, with a compliment, which is to say that this is super interesting work and obviously very important, and kudos to you and your team. So as a patient, people probably have different personal values for the epsilon that they might want to set because of whatever it is. Some people just post their DNA online, and here's my X-rays and whatever. And there's a huge spectrum, right? And so so is that envisioned as being part of the part of the input or not? Or?
Obviously, with accessibility comes responsibility. And so it is really we need to educate patients on the risks. So they need to learn about what the risks are. So that's the first, and that's part of our strategy, is to sort of educate what are the risks, explain what could happen if they because people don't think about it. And a lot of the times also, what we have found is, from the literature, is that not only do either they don't think about it, or they kind of feel like they're hooped anyway, like we're being surveilled anyway, so there's nothing to do, so let's just kind of go with it. And I think just showing them that there is an option, that's going to be very powerful, and educating them on what their options are and what it means. And again, that's partly why we really want to make sure that these parameters are interpretable to the patient so that they're able to set this dial intelligently. But the other thing is, from a technical standpoint, it is conceivable that they could have a dial for every single field, and every patient could have a different dial, and the whole system will deal with that. Now, is this something that's reasonable that we could expect from patients to do, to go field by field and set a dial? Probably not, but it is possible technically.
And also, because DP has that nice composition property, maybe it's a little bit harder at the patient level, but you can do it at the site level, where different sites have different values for epsilon, and then when they get aggregated, you just add the values of epsilon, and then that's the privacy for that query you're making. Yeah. Okay.
Cool. Questions about the current system. So in the DP option, you actually cut people off after a certain number of queries?
So you could cut them off, but we're not planning to cut them off. So currently how DP is implemented in practice, so for example at Apple, actually they reset the budget every day. So it's kind of cheating, right? It is a little bit cheating. We don't want to do that. So one of the things that we're thinking about doing is that, so we're going to work with synthetic data. That's the plan that we're hoping to implement in our budget optimization, is work with the synthetic data, and as the budget, as you run out of budget, replace the real data with the synthetic data, because that's already DP and it's already been sort of exposed. And so you could replace the real data with the synthetic data, so you're not really losing everything. You're not throwing out the baby with bathwater, but you are still protecting the patient. So coming up with little strategy like that of caching queries and using the synthetic, really employing the synthetic data to our advantage is the best way that we're thinking to extend the life of the data without. And so we're hoping that as these systems become safe, and accessible to everyone and so on, more and more patients will join, and we're not going to run out of data to train on. I think the reason why right now it's difficult to find data, in the medical system is because it's very difficult to get patients to consent. It's very difficult to get studies to recruit. When this becomes part of standard of care, we may not face the same problems.
Some countries like China, for example, have a lot less privacy laws than North America and the European Union. For their medical data and their medical research and studies, have they been moving ahead very strongly, and have they had positive results, or has it turned out to be a bit of a disaster among their population? Do you have any insight into that?
Definitely they have less privacy laws, and definitely and they have numbers, and so that's enabled them to move a lot faster than other parts of the world. And I'm not really sure exactly onto whether or not that had negative repercussions on their population with respect to privacy breaches and that sort of thing. With respect to results in terms of accuracy of models and all that, then yes, all of the big studies are actually coming out of China. So it is really, we should really solve this problem, and so that we're able to compete on the machine learning algorithm side of things.
Okay, why don't we thank Aline again?